Welcome to the 26th lecture for Physics 4B. We finally introduced the driven AC circuit in this lecture. We start this introduction with examples, looking at the voltage divider circuit with resistors, inductors, and capacitors. We use Kirchhoff's loop rule to write down the equation of motion for the circuit, which we solve with calculus. Our main goal in these lectures is to introduce and acclimate to the concept of complex impedance, which greatly simplifies AC circuit analysis, even more so than the phasor-based approach in the textbook. We will in particular use the example of LR circuit to demonstrate how use of complex exponentials and complex impedances simplify the analysis. We end this lecture with a recorded demo of an LRC circuit resonance, which we will explore more in our second lecture on the driven AC circuit. So I have about 20 minutes, and in that 20 minutes, what I want to show you is so if we were to take upper division circuits class, so what we are talking about now is something called the linear circuit element. It's something that's supposed to be very simple, something that doesn't require a lot of advanced mathematical techniques to work out. But what you have seen so far doesn't look that way, because what you have seen is that once we introduce the capacitors and inductors, then we had to start using tools of calculus, right? And so what I want to show you is how we are going to turn the clock back so that when you have circuits that deal with the inductors and capacitors, we are going to be able to answer some important questions about these circuits using nothing but algebra. No calculus, just with algebra. So I will work this out using calculus, and then you will see that with a certain identification of particular concept that we would have called complex impedance, that what used to be calculus problem turns back into an algebra problem. So let me do this RR circuit, which is not a real thing, as the resistor circuit, so that you see the method we are going to apply throughout all these three problems. And then I'm getting at a particular result that I can point to and say, using that result, we are going to come up with an idea that will allow us to solve these portions of questions using nothing but algebra. Well, complex number algebra. Okay? So these are all voltage divider circuits. Do you recognize this as the voltage divider circuit? Yes? You've seen voltage divider several times now. You saw it in the DC circuits lab. And if you've been working through homework, you've seen a voltage divider. It was on your exam too. One of your exam 2 multiple choice question was a voltage divider circuit. So if you haven't seen voltage divider, that's because you haven't been studying. It's not because you didn't have a chance to see it. So we call this a voltage divider because when you work through this circuit, call this voltage in, call this voltage out, and the formula for voltage out is actually ends up being this pretty simple formula, R2 over, so the resistance here divided by the total resistance, R1 plus R2, times the input voltage. Like, this is the formula that you have seen, you have derived. And I guess in the interest of time, I'll leave this here. You guys know how to get at this formula using at least a couple different methods. You could get at this formula by first figuring out the current, that the current going through here is the applied voltage divided by the equivalent resistance, and then multiply that with this, that would get you that. Or you can use the entire Kirchhoff's rule arsenal here. So, but what's important here is that this is the formula you end up with. And what I want to do in the remaining time is I want to go through this LR circuit and the RC circuit properly so that I'm not using any shortcut. And we are going to look at the result and see that the result reminds us of something, so that if we introduce this particular concept, then it's a shortcut that you can take when you're analyzing circuits of this kind. So for all of these circuits, they have to have one same characteristic. It's that they have to be a driven circuit. So really what I should have said is this is a driven LR circuit. This is also driven RC circuit. And this is what it means by being driven. This voltage source, it's an oscillating voltage source. So this voltage input is going to be in the form of some oscillation amplitude times cosine of omega t or sine of omega t. But because I know what I'm going to do, I'm going to use e to the I omega t to represent the oscillating portion of that voltage source. Okay? So some amplitude times e to the I omega t is the input voltage. And if you are uncomfortable with these complex functions, what you can always do is imagine taking the real part of this, and you say, well, that's what I really mean. So, if I want something that's oscillating like sine of omega t, I have to make my v naught imaginary, so that the whole thing will come out to me. Good? So for the rest of the calculation, I'll just keep these complex functions as it is, with the implicit understanding that if you ever want to get back to what you do literally measure on your oscilloscope, you just take the real part. Good? Okay, so I want to find the voltage output here. So I'm going to go through the motion of Kirchhoff's rule, the law application, to find the voltage here. So to find the voltage there, I can say the voltage out, it's a voltage across the inductor. So I should be able to say this. The voltage across the inductor, as a function of time, is equal to the inductance times di dt, still a function of time, right? So what I should do is I should try to get an expression for current I, and then I can take the derivative and figure out this voltage across the inductor. So it does come down to the same thing, same old thing that we do every single time. We consider this loop, say there's a current flowing around this way, apply Kirchhoff's rule to find the value of the current, and then once I have that, then this is a single step thing. Okay? So let me write down Kirchhoff's loop rule. The loop rule says that when you add up all the voltage changes as you go around the loop, it should add up to 0. And this time you have a time-dependent voltage applied, but that doesn't change Kirchhoff's rule. This is a general circuit solving method. It's equally applicable when everything is time-dependent, as it was when it was just a DC. So let me write it down. As I go across the voltage source, so I gain this much voltage. So plus V naught e to the I omega t. As I go across the resistor, I lose some amount of voltage, call it minus current I as a function of time times R, right? As I go across inductor, this time I guess this time and every single time, I lose some amount of voltage as I go across the inductor. So as I go across the inductor, I have minus L times di dt, and all of this should add up to 0. Everything good? Yes? All right, so, this is an inductor circuit, so it's actually pretty simple. There's no capacitor there, so no Q to worry about. All I have is current I. So that's the only unknown. So I'm going to have, so I don't need any other equations. This is my one equation that I need. So to solve for current, I guess what I'll do is the same thing that we did for last couple times. We are going to guess what current I is. I guess to justify why we are not using separation of variables, like we did last time when I was dealing with this first order differential equation, is that this time I have this term here. I have something that now explicitly depends on time. So you will find that if I try to do separation of variables here, it doesn't work because of this term here. I think it's called the inhomogeneous term. Whatever. So separation of variable doesn't work. You can try it on your own time. It doesn't work. So what I'm going to do is I'm just going to give a guess. And as I have been intimating a few times now, the convenient guess us physicists have every single time is an exponential. So I'm going to guess that, in fact, I'm going to be a little bit more specific. I'm going to guess that my current will look like this. It'll be some I naught, some magnitude of current. It'll be constant, but it may be complex, times e to the I omega t. So I think because my voltage source is oscillating at a particular frequency omega, that the current is also going to oscillate at the same frequency. And if it doesn't turn out to be this omega is a constant, we'll figure out what it is. But I'm going to put it in this format because I think that's what it's going to end up being. Yeah? Or I guess if I want to be sure, I can call it omega prime and do it later. But I'm pretty sure, so I'll just leave it as omega. Let me rewrite this one more way. In fact, I can rewrite this constant complex coefficient in a way that it separates our two aspects well. I can rewrite this as the real value I naught times a phase factor times e to the I phi. So that this is a two parameter complex number, but each of them, the parameters have a very clear meaning. This is the maximum value of current. This is the, on which cycle are you starting? Is the current varying as cosine or sine? Okay. So let me use this as my guess. So I'm going to plug this in here, see what I get. So let me do that. Plug it in here. So the first term doesn't have any I in it, so it'll be V naught e to the I omega t minus I times R minus I naught e to the I phi times e to the I omega t times R minus L times the first time derivative. Well, it's an exponential, so the derivative is simple. When I take the derivative, a factor of I omega comes down. So it's minus L times I omega times I naught e to the I phi e to the I omega t is equal to 0. Good? Yes? Okay, let me cancel out a few things that cancel out right from the get-go. E to the I omega t cancels out. It's in every single term. In fact, if you are making mathematical argument, that's what you would do. You would start out with omega prime, and then you would say, well, the only way that to add up to 0 for every value of t, omega prime has to be equal to omega. All right. And I guess that's all that cancels out. So what I'm going to do is I'm going to solve this for current I. Oh, so I guess this is really the main unknown that I'm trying to figure out here. I'm really trying to figure out this I naught. Yes? So, yeah. So let me do that. In fact, I'm going to solve for this I naught times e to the I phi. So I see that term here, and this term here. So let me factor it out. When I factor it out, this is what I end up with. V naught minus, this factored out, I naught e to the I phi times R plus this here, I omega L. All of that is equal to 0. And when I solve for the current, this is what I end up with. The solving for this, I naught e to the I phi is equal to, so move this over and divide it through by this. So it'll be V naught over R plus I omega L. In fact, let me change up the plan of what I was going to do. I see that I only have 5 minutes left. And let me give you an equivalent problem that I can do more quickly. This is really how I should have done. So here, what I've done is I've essentially solved for the current here, right? I have these coefficients. I multiply by e to the I omega t. That's my current as a function of time. So I'm going to compare this to the expression for the current here. So the expression for the current that's going through this circuit will be the V in as a function of time divided by R1 plus R2. So it will be V naught e to the I omega t over R1 plus R2. Or So this is the current with this time dependency here. Or if we write it the same way we did it there, it'd be I naught times e to the I phi is equal to, and this got canceled out in the derivation process. So you have this V naught over R1 plus R2 as the maximum amount of current that flows through here. Okay. So this is what I want you to see, that this expression looks bears some resemblance to this expression here. Let me do this for one more circuit, the RC circuit, to see that this resemblance it doesn't stop here. So let me do one more. So with the 3, it will be easier to spot the pattern. So let me do this for the RC circuit. So for the RC circuit, this is what it looks like. So I'm going through the Kirchhoff's rule all over again. So say sum of all the voltage changes through the loop, say that's equal to 0. So this is the loop I'm thinking of. So the sum of all the voltage changes is my applied voltage, V naught e to the I omega t. As I go across the resistor, I lose some amount of voltage, minus I times R. As I go across capacitor, does the voltage drop or rise? So here, as you're charging, the voltage will drop. Because if it's imagine positive current flowing, this will be positively charged, this will be negatively charged. So as you go around, it's going to be a voltage drop. So you are going to have minus Q of t over C. So all of that is equal to 0. So we do the same thing that we did the last time. So here I will just have to give you the answer. The current I of t is going to be just the dq dt, no minus sign in front. Or you could say it's plus dq dt that gives you the correct sign. So with this the loop rule equation ends up being V naught e to the I omega t minus R dq dt minus Q over C is equal to 0. So here we do the exact same thing that we have done so far. We guess an exponential as an answer for this Q. We say Q as a function of time. Q as a function of time, we guess it's going to be some maximum amount of charge and times e to the I phi, the phase factor, to account for the fact that this constant is going to be a complex number, times e to the I omega t, oscillating at the same frequency as my applied voltage. So when you plug this into this differential equation, this is what you end up with. You have V naught e to the I omega t minus R times this omega t, or I omega comes down. So minus I omega R, I guess that's it, times Q naught e to the I phi e to the I omega t. That's the second term. And the last term, minus Q over C. So Q naught over C e to the I phi e to the I omega t is equal to 0. Yeah? So I can solve this for Q of t. So solving it for Q of t, this is what you end up with. Q of t, so this is Q of t, and so this is Q of t. Solving for Q of t, I get, just algebraically, I get, this is equal to, so, well, let me not skip too many steps. I've already skipped it, many steps. So let me combine these two terms and factor out Q. Then I end up with V naught e to the I omega t minus factor out Q of t times this term here, I omega r plus this 1 over c. 1 over c is equal to 0. Let me solve for Q of t. Q of t is equal to V naught e to the I omega t divided by I omega r plus 1 over c. Okay? To compare the result here, I need to take one more step because I'm trying to compare to the current. So I need to use this expression here to take one more derivative. Take this, take the derivative with respect to time, then what you see here is that all this is all constant. V naught is constant, I omega r is constant, 1 over c is constant. So here the time derivative will simply bring down a factor of I omega. So that you end up with this. All of this is, so that you end up with current, or dq dt is equal to this times I omega. So I omega times V naught over I omega r plus 1 over c times e to the I omega t. Let me do one simplification. I'm going to multiply divide top and bottom by I omega. So that this is equal to V naught over I omega cancels, r plus 1 over I omega c times e to the I omega t. So this is, for this RC circuit, this is the current through the circuit as a function of time. And when you look at here, I really should have done the same thing across. Sorry, I'm switching back and forth. My apologies for this confusion. So if I want to describe here, if I want to describe current as a full function of time, then I should take this and multiply back this e to the I omega t. So let me write that down so that I can compare the same expression throughout. Current as a full function of time is V naught over r plus I omega L times e to the I omega t. And here, the current as a full function of time is equal to V naught over R1 plus R2 times e to the I omega t. This is for the 2-register voltage divider circuit. And with these three expressions, this is what I want you to look at. When you look at these three expressions, you will see they share some common features. They all have the same voltage V naught. In fact, they all have the same V naught e to the I omega t. That's my applied voltage as a function of time. So I can go one more step to try to make this look simple. Let's say combine these to say this is the applied voltage as a function of time. Here I say this is the applied voltage as a function of time. And this is applied voltage as a function of time. Then this is what I'm hoping you are noticing. That so for all three expressions, the numerator looks identical. The only differences are in the denominator. But even when you look at the denominator, some parts of the denominator are still the same. Which part is the same?
The beginning resistance.
The R1, right? It's the same R1 resistor that's in all three circuits. So this part is the same for all three of them. So this is the identification that I want you to start making. So in this class, we don't have enough time to, so this is the, if I had 20 minutes to more, this would have been the beginning of the discussion of complex impedance. But to bring this particular thread to conclusion, let me just point this out. This is the quantity that we are going to identify with a kind of resistance. That's easy for R2, that is resistance. I'm not doing anything new here. Whether voltage is a function of time or not, nothing funny happens here. Something interesting happens with inductor and capacitor. We are going to associate this with a kind of resistance that we can associate with inductor. So this is what we call impedance. So if you want to look up the word for it, so this is what's called the impedance of an inductor. It has two features in it that I want you to notice. It depends on omega. It depends on the frequency of the signal that you are applying. So that's why I had to assume that my voltage is being applied at some particular frequency. And the second thing is it has a I in there, imaginary number in there. So this is what we call complex impedance. In your textbook, they will try to cover this in terms of phasor. So the phasor for the impedance of an inductor, it's going along the y-axis or something. For me, when I saw that, when I was studying lower division physics, none of them made any sense. When this actually did make sense was when I was teaching when I was taking upper division circuit class, where all of this is described in terms of the complex impedance. That's where the math is simpler and it's easier to make the connections. So this omega L, I omega L is kind of a resistance we associate with inductor. And it sort of makes sense. The higher the frequency, the inductor resists current more. Because the change of current has to happen faster, so the voltage needed across inductors are larger. And this one is maybe a little bit harder, that's why I'm doing it the last. This 1 over I omega C is the kind of impedance for so this would be the capacitor impedance. So that's what we associate with. So I don't know. This one is a little bit harder to give an easy meaning to. So with the capacitor, I guess one thing you can say is that if omega is very large, if the voltage is switching back and forth quickly, then the amount of voltage drop across the capacitor is very small. You could understand it as maybe the amount of charge building on the capacitor being very small. Before any amount of charge can build up, the voltage flips and it drains again. But so once again, if we had 20, 30 more minutes, we would talk about impedance more, but I'll just leave that there. And this is sort of the reason why I introduced the complex numbers on Monday. In order to get this far at least, we have to have the complex number description. And there's a reason I can simply write this down without doing any other calculus. And this was the intent last time, which because it was so rushed, we didn't spend a lot of time. What I wanted to do last time was with the comparison of these terms that I'm boxing that you would get from going through calculus, to highlight that there's something useful that comes out of this treatment of the driven AC circuit using complex exponential. That you get you obtain a quantity which is actually it's an imaginary quantity if you are dealing with inductor or capacitor, or if you want to include the resistors, then it's actually complex quantity. This is a quantity that could be real, imaginary, or maybe even combination of both. Because when you look at this, so when you look at R1 plus R2, what you would have said is that this is the equivalent resistance of the resistor plus the other resistor in series, right? And in a similar way, you would say this is something that's similar to an equivalent resistance of these two circuit elements in series. The difference here is that this is a complex number. It has a real part and it has an imaginary part. Yeah? So I think this is really where we left off last time. I ideally should have had time to introduce complex impedance, but we sort of abruptly left. We got as far as this, and then you guys at least got to see the similarity between the expressions, and you got to see at least this far of the expression, I⍵L and 1/I⍵C. That actually should be in your notes. And that occurs in a place in an equation where it can be compared with R2. So the intuition that we are trying to build up there is that this is a quantity that behaves like resistance. Okay? So let me actually introduce the term that your textbook does use, except your textbook doesn't say the word complex. So this resistance-like quantity. So we are trying to generalize resistance. What is really nice about resistance is that recall back to like 2 months ago when we introduced the resistance. How did we introduce resistance? Like, how was resistance defined? Pedro, how was resistance defined?
Voltage over current.
Okay. Do you remember the name for that definition? Ohm's law. Yeah. I mean, voltage over current is right. But so knowing the names is important. I keep trying to emphasize it's not enough to memorize the formulas. You have to know what formulas mean. And part of remembering the meaning of the formulas is in remembering their names, the entire story behind the formula. So this is how resistance was introduced, right, in Ohm's law. And one of the surprising thing about Ohm's law, by the way, with the quotation mark around the law, is just how simple it looks. It says, resistance is voltage over current, or this establishes this remarkably simple relationship. It establishes this relationship that voltage is equal to resistance times current. That voltage and current are linearly related to each other. They are simply proportional to each other. And what we have lost since then with the introduction of inductors and capacitors is that simple relationship. Because we have now introduced the calculus into what used to be simple linear algebraic relationship. We have introduced things that must involve calculus. And same thing here. It doesn't look calculus-y, except the only way to relate current and charge is to say current is dq dt. So we had a simple relationship that got ruined. And the new concept we are introducing now is the attempt to restore the old simple picture. So this is the idea or the motivation behind introducing something called impedance. It's so intuitively what it is, it's a generalized idea of resistance. Whereas resistance will apply only to, well, resistors. Impedance can be used to describe property, characteristic of resistors, inductors, and capacitors. And the way I teach this section of the class, I am always going to call this complex impedance, because impedance is a complex number. In your textbook, they will try to cover this with the phasors. So in a phasor diagram, this is a diagram that you might find in your textbook. The phasor diagram in your textbook might look like impedance phasor will look something like you have x and y axis, and they will tell you that impedance for resistor looks something like this. This is the impedance for resistor. Impedance for inductor looks something like this with the length omega L. And impedance for capacitor looks something like this with the length 1 over omega C. I mean, you can do it that way. But as I was trying to say as we are rushing through last time, all of this is really very contrived way to describe something that is naturally described as a complex number. If you describe impedance as a complex number, then this x-axis, all it is nothing more than the real axis of complex plane. Y-axis, all it is nothing more than the imaginary axis of complex plane. And all these can be described by a single complex number, where the impedance of resistor is simply R, and impedance of inductor is, so it has this omega L in the imaginary component, so that would be I omega L. The capacitor, it has imaginary component in the negative direction, so minus I over omega C, or 1 over I omega C. So let me write down these complex impedance formulas that I will justify at least using this example in detail, because I think that was one of the things that we lost. So these are complex impedances. For the complex impedance, we are going to use the letter G. Don't know why, it's standard symbol. And I'm just going to write down the squiggly on top when needed to indicate that this is a complex number, the way we handle it. So impedances can be used to describe resistors, inductors, and capacitors. So with the resistors, it's talking about the impedance of resistor. Well, it's just resistance. It's just the old idea of resistance is folded in as a special case of an impedance. So impedance of a resistor. This time I'm going to write down squiggly line because it's a real number. That's simply the resistance. So nothing new there. What is new is what I'm going to describe as impedance of an inductor. So impedance of an inductor, L, is going to be I omega L. So it's a quantity that's like resistance in many different aspects. Quantity that is like resistance in many different aspects that we are now going to properly give it a name, call it impedance, and this is a complex number. And we'll see how that works out in our calculation. And for capacitor, the impedance of a capacitor is 1 over I omega C. And I guess normally you would just memorize this as the formula for impedance. You can you can derive them. To derive it, you'd go through this calculation that we went through last time. When you go through the calculation, you identify this term, which if you could call it resistance, everything would work out so nicely. So you call it impedance, and identify this with the impedance of inductor, and identify this with the impedance of capacitor. So with this introduction of impedance, this is what we can now say, and this is the whole reason for introducing impedance. So we had this beautifully simple relationship before that got ruined by introduction of all these time-dependent circuit components. Now we are going to restore that old beautiful relationship again. We are going to now be able to say with these impedances is that voltage as a function of time, as a complex quantity, is equal to the impedance, which is a constant. It can be imaginary, real, complex. If we have two circuit elements in series, you can get complex impedance. So voltage will be impedance times current as a function of time. So this is a relationship. This linear relationship is what we are trying to restore, and that is the motivation for introducing this idea of impedance. Yeah?
The idea is that this voltage gets plugged into the Kirchhoff rule?
No, I mean, so really what we are trying to do in introducing impedance is that I don't want to go through Kirchhoff's rules again. Because you remember how simple it was to solve this question. You didn't have to go through Kirchhoff's rules. You could just simplify this as equivalent resistor, R1 plus R2, get the current, voltage over R1 plus R2, multiply by resistor, R2, get the voltage out. You could have done it that way. The reason we couldn't do it here and here was because, well, because it takes a lot of, because it involves calculus. And the goal, it involves calculus as you go through Kirchhoff's rules. The hope is that as we introduce this, we might be able to avoid having to use Kirchhoff's rules in some of the simpler circuits. So let me use this circuit in particular as an example for really two reasons, I guess. One is to validate this approach. That this approach, so I was running into this last time. With a limited amount of time we have, you won't have enough time to build up your faith to the degree I have on this formulation. But what I'll be able to show you is that, let's say if you are trying to solve for current, then you can get to that result in three different ways. One, super difficult way using only real functions. We'll do that with the LR circuit. Two, a somewhat easier way that still uses calculus. That's what we did the last time. We'll do it one more time in more detail. And three, using this relationship simply algebraically. And all three methods will yield the exact same result. So that's what I want to show you, because I feel like the reason many instructors skip AC circuit is because when you use the first approach, which is what your textbook does, it is mathematically complicated. But I believe it's only mathematically complicated because you're using rudimentary tools. It's like trying to nail in a screw with a hammer when what you really need is a screwdriver. And if you had a power drill, then that's the easiest thing in the world to do. But because in your textbook they are being forced to nail in a screw with a hammer, it's so difficult and a lot of instructors skip it. But I think these are not advanced mathematical tools. It should already be in your toolbox. If it's not there, you should get it now because it's going to come up soon anyway. So with this, I think you can actually look at this LR circuit and see how easy it is to analyze it. It's not hard at all. So let me actually do the LR circuit 3 times. So I'll do it first the hard way. And the reason really your textbook doesn't cover it. So let me call this LR circuit analysis, try 1. And this is probably how we should have started the last time, but I'll do this anyways now so that at least I can say you have seen it. So the way of handling it this time, it'll be my input voltage. I'm going to keep to real functions. So my input voltage is V naught cosine of omega t. That's something you can easily visualize. And that's hooked up to a resistor and an inductor. All right, and I think this is what we did the last time, and I will do this time also. The question that we want to answer isn't the voltage across it. Well, actually, let's do it both ways. So we'll answer 2 different questions. The final question that we'll answer that can actually relate to the circuit demo that you have up here is what is the voltage across the inductor? That's a question you can ask and get an answer to. But an intermediate question that we should answer to get to that is what is the current flowing through the circuit? Good? If you knew the current as a function of time, how would you get this voltage output? Yeah, rate of change of current. So this is a very simple step that we can apply to get the voltage output across the inductor. Once we have the current, so we are going to treat this as a simple, just the last step thing we can do, and we'll focus most of our time on finding the current as a function of time. Because once we have that, then this is an easy question to answer. So let's focus on that question. What is the current as a function of time? So this is where we do have to use Kirchhoff's rules. So let me just set it up, and I mean, you've seen this multiple times, but let me just set it up so that I'm not leaving anyone completely behind. So Kirchhoff's loop rule says that when you go around in a loop, collecting all the changes of voltage, then the voltage change should add up to 0. So go around the loop, collecting all the voltage change. As I go across the power supply, I'm going to collect this voltage rise, V naught cosine of omega t. As I go across the resistor, I'm going to get voltage drop of minus IR. I'm writing this in to remind me that current is a function of time. And as I go across the inductor, I'm going to get voltage drop according to the expression that we discussed, minus L di dt. So all of this should add up to 0. That's what the loop rule says. So I'm using LR circuit because it is actually mathematically simpler. Once you write down the loop rule, then you realize, oh, that's all I need. I have one unknown, current, and I have some differential expressions indicating this is a differential equation. Good. So let me put this into the form I have been putting all my differential equations into. I'm going to solve this for the highest order differential. So di dt is equal to, so move this over, divide out by L. So it'll be V naught over L cosine omega t minus R over L I as a function of time. But I won't write t here. I want to draw a distinction between things that are explicitly function of time and things that are not explicitly function of time. So when you look at this, and actually this is the one that's similar to your quiz, before you use the separation of variables, right? Yes? Yeah. So before you could do that, because when you looked at expression here, nothing depended explicitly as a function of time. So you could essentially move the whole thing over to the other side, move t over, and do that. Now you cannot, because this is now an explicit function of time. So when you move the whole thing over, you have not separated the variables. So this really gets in the way. I don't know if I remember the right terms. Inhomogeneous, I think it's just a linear differential equation. Mathematicians probably have some term for it. But what it comes down to is that for us, separation of variables, which is the only direct way that we know of solving differential equations, doesn't work here. So what approach does it leave us to try to solve this differential equation? Crystal, what approach remains for us to try to solve this differential equation? Yeah, we just simply have to guess and check. So let me quickly go through some of the more naive guesses that won't really get us to the answer. So here's one naive guess. You might guess that my current as a function of time is something sinusoidal, right? Because you intuit enough that if my voltage is oscillating, this is going to oscillate. So you might say it's some amplitude times cosine of omega t. And as you try to plug this in, you will see that there's no way this can work. Let me just write it out so that you can see that it doesn't work. So let me plug it in. Left-hand side becomes derivative of this. So it's minus omega I naught sine of omega t. That's the left-hand side. First time derivative. I'm trying to say that's equal to the right-hand side, v naught over L cosine of omega t minus r over L I, or I naught cosine of omega t. That doesn't work. Because when I simplify the right-hand side, it becomes this. V naught over L minus r I naught over L times cosine of omega t. I have sine on the left-hand side, cosine on the right-hand side. Sine and cosine don't cancel. They are not the same function. So, all right, so that won't work. What else would work if sine and cosine don't work? I mean, so if cosine wouldn't work, so here's really the difficulty. Before, when you are trying to get a solution to a similar differential equation, the only thing we are dealing with was the second order derivative. When you take two derivatives, cosine goes back to cosine. But here now we are having to deal with the first order derivative, which creates a lot of problems with the trigonometric function. Let me try to give you some intuitive motivation with this circuit, which illustrates this exact setup. Part of intuition is simply knowing the answer. It doesn't matter how you know it. What's important is that you know what the correct answer is. I mean, if you had to give a definition of physical intuition, it's really nothing more than that. It's knowing the answer without having to calculate it. If you had to calculate it to get the correct answer, then you don't have an intuition. That actually describes a lot of mathematicians and some theoretical physicists. And sometimes that approach works, but I'll tell you that some of the best engineers and best physicists have plenty of physical intuition, meaning they didn't have to go through a lot of complex mathematical expressions to know the answer. They could simply guess the correct answer. So, for most of us here, you don't have that intuition yet. That's why you are still in school and not in, government research. So let me show you the answer. Try to build our intuition from that. So what I'm going to do is, so I have this circuit set up here. So what I'm going to do is I want to have an answer for current. So what I'll do is I'll measure voltage across the resistor. That'll give me something that I can relate to as a current. So let me apply the voltage. across the, so this is inductor and resistor in series, in case you haven't realized it. So I'm applying a voltage now, and I will measure the output voltage across the resistor, which will be something proportional to the current. And what I want you to see right now is the oscilloscope picture. All right. So let me set up the highlight some of the features so that you can distinguish. Right now it's showing both outputs. So as usual, my input voltage is going to channel A. So let me just turn off and, actually let me turn off channel B. So this thing that you see me turn off and on, that's my output voltage across the resistor. So I'm applying the input voltage, something sinusoidal. I guess I can change it so that it looks like a cosine of, so it looks kind of like cosine of omega t, right? So let's look at what the current looks like. The current, which is represented by this input voltage, does it look something like a cosine, as it's something oscillating? It is an oscillatory current, right? In what way is it different from the applied voltage? It's lower, so it might have different amplitude. I've accounted for that before. So in what some other way is it different from the applied input voltage? It has shifted. So the input voltage maximum happens here, but the current maximum happens here. That is the biggest difference. That this current, it is still something oscillating. So it should be possible to describe with a cosine and sines. So what I'm hoping that this is making you realize is that our guessed solution was missing one term. So it's not why not cosine of omega t, but I have to include a phase factor to account for the possibility that the current that we get will not have the same phase as the applied voltage. Good. This word phase is really where this phasor diagram gets its name from, but I don't know. I never liked phasor diagram. So anyways, let me use this new guess. So our new guess now is still cosine, but it has this phase factor, and that's going to give us some possibility to see if this can be correct answer to this. So let me write it up. But even with this correct guess, it's still going to take a lot of math. That's once again why. The only reason I'm doing this is to show you that learning all this new mathematical tool is worth it, especially if you're dealing with the circuits. So just plug it in, take the derivative. So I get, well, same derivative last time. So it's minus omega I naught sine of, well, inside it doesn't change. So it's omega t plus v. I already took out a factor of omega from the chain rule. This is the left-hand side. And the right-hand side is this. So v naught over L cosine of omega t. This is applied voltage. So just cosine of omega t minus R over L. So I, so cosine of omega t plus phi. All right, staring at this expression, can you easily see that this left-hand side expression is equal to this right-hand side expression? I can't. So this is where you need to do additional mathematics. So what I would do is you have to use a sine, cosine, angle addition formula to take this expression and re-express it as a sum of sine and cosine. Take this expression, re-express it as a sum of sine and cosine. And then you collect like terms, collect terms with the cosine, collect terms with the sine omega t. And you can say term by term, those coefficients have to agree. So that's the mathematical step you have to go through. It's not, I mean, it's tedious, but once you realize what you have to do, it's not that hard. Everyone here remembers the sine and cosine angle addition formula? If you have not yet have it memorized, I really recommend that you have it memorized, commit it to memory. This is the single most important trigonometric identity, which says cosine of alpha plus minus beta is cosine of alpha, cosine of beta, minus plus sine of alpha, sine of beta. Sine of alpha plus minus beta is equal to sine of alpha, cosine of beta, plus minus sine of beta, cosine of alpha. For those of you who cannot commit this simple expression to memory, let me tell you one way where you can avoid having to memorize this. One way you can avoid having to memorize this is to build familiarity with the complex exponential. Because this is really why people introduce complex exponential. It simplifies all your math once you know how to learn how to deal with a complex number. With this formula in tow, what you do is you would express cosine of theta in terms of complex exponential. E to the I theta plus e to the minus I theta over 2. And everything that's expressed in the trig identity, it comes down, you can work it out using exponential algebra really easily. But anyways, that's probably more of an upper division material. So let me use this formula to simplify this and see what I get. And see if I can get a result that's more reasonable. So I have to rewrite this. So this left-hand side will be minus omega I naught times, I guess I have to go through step by step. So sine of, I'm using this trig identity here. So it'll be sine of omega t cosine of phi plus sine phi times cosine of omega t. All right. I guess I better simplify because my expressions are going to get super long and complicated. So let me collect them in with their respective like terms. I'll write down the cosine omega t term first, and then the sine omega t term. So this is equal to cosine of omega t times this times sine of phi minus omega I naught times sine of phi and plus the sine of omega t term, sine of omega t times this times cosine phi. So minus omega I naught cosine of phi. All right, so this is my left-hand side. I have to work out my right-hand side. So let me write this out first. And then we'll try to identify some coefficients together. So right-hand side is, well, I guess, I can just write this down. I don't have to do any work there. V naught over L cosine of omega t. And then this, I have to expand out the same way I did it before, this time using the cosine angle addition formula. So minus R over L times, all right, looking at that, it's cosine of omega t times cosine of phi minus sine of omega t times sine of phi. All right, I have to collect like terms like we did before. So let me do it for the cosine omega t term first. I'll combine the like terms as I'm doing that. So cosine of omega t is equal to V naught over L minus, I feel like I missed something. Aha. There's this term I naught here that I forgot. So there should be I naught here that I forgot. It's complicated algebra. All right, so cosine of omega t times all the like terms together. So V naught over L minus R I naught over L. By the way, this is something you should get into habit of doing. The reason I could see something was wrong here is the unit of R over L doesn't match the unit of V naught over L. You need to be constantly checking your expressions for units. That's how you know when you made an algebra mistake, like I just did. Okay, so that's the cosine of omega t term. I need to write down the sine of omega t term. So minus and minus, so it'll be plus sine of omega t times, well, I guess the only thing, R I naught over L times sine of phi. All right. It's tedious, but it's mathematically doable. So left-hand side is equal to right-hand side. And for that to be true, left-hand side depends on as a function of cosine of omega t and sine of omega t. And the argument that you would make here is that the only way this equality can hold for all values of time t is to say the coefficient for cosine of omega t term must be exactly equal. And coefficient for sine of omega t term must be exactly equal. So what you would be able to say is you can set up this system of algebraic equations. You can say this term here is equal to this boxed term here, and which would give you this expression here. Minus omega I naught sine phi is equal to V naught over L minus R I naught over L. Oh wait, there's a cosine. Yeah, that's what you're talking about, right? Cosine phi. This cosine phi that I forgot to write down. Once again, there's a reason I don't like to do this. It's complicated, and complicated means a lot of chances to make mistakes. So good. All right. And this is the first equation, and the second equation comes from saying that this coefficient must be equal to this coefficient here. So you say, all right, minus omega I naught cosine phi is equal to this. R I naught over L sine phi. This is a system of two equations involving two unknowns. It's, once again, tedious but doable. The two unknowns are your I naught and phi. So you can solve for I naught eliminating phi or vice versa. So let's see. Do I want to go through this? I should. We'll go through it and then take a break after. Well, let me put it this way. I mean, you have a system of equation, and the rest is simply going through the math. So let's take our 8-minute break now, and during the break, I will simply write down the result here. You don't really need to see me go through the math. I only need the result to quote. So if you want to take the break now, please do. Come back by 2:10. I will have the answer to what I naught and phi is written down here with all the steps in between. So I'll just work it out quietly. All right, right on time. Welcome back. So this is the result. I had to do over the algebra twice. Well, once. So the algebra is, it's not easy algebra. It's tedious. You have to know the exactly right thing to do. And in case you want to work through it on your own, let me tell you the exact right thing to do. The exact right thing to do is to realize that in the second expression, I naught actually cancels out. So the second equation actually gives you an expression for phi right away. And this is something you should use to simplify the first expression and eventually solve for I naught, cosine of phi, draw the triangle to express it algebraically in terms of R and omega L. So once you do that, plug it in, then this is the simplified current expression. So I naught is equal to V naught over this. So coming back to this answer here, what we would say is that for this guess to be correct, we have to say this I naught is given by that value that we found by solving the expression here. So we should say this is equal to I naught or V naught over square root of omega squared L squared plus R squared. That's the amplitude. That's the reduced amplitude you saw. And we still have this cosine of omega t plus phi. And I guess I'll just leave it here. So this phi is, instead of being an undetermined value, it's actually determined. This is the expression that determines the numerical value of phi. And I could plug in, phi is the arctangent of minus omega L over R, but you know what, it's getting complicated. So I'm just gonna leave it there. So that's the answer. And so I'm going through this to show you that this is all doable without introducing any of the new mathematical tools that we have introduced. You can actually do this all. It's not impossible to do. It's tedious. It does involve an insight that you may not have known before, but it is doable. But all this tediousness, that's really the reason many instructors for this class don't cover driven AC circuit. Because they realize that to make students to go through this math, that's not something that you can ever put on an exam. Because this is way too time consuming for an exam. Doable for homework, but way too time consuming for exam. So this is what I'm telling you. With the mathematical tools that we are introducing, all of this gets a lot simpler. So I said that I will do this circuit 3 different ways, right? This is the first method. It took, half of the class or something like that. What I'll show you is the second method, which is actually a very simple improvement from using a real function to complex function. Already simplifies my work a lot. So let me, so I think I'm actually going to leave a lot of the expressions in place, and I'll just make modifications. Modifications for using this complex input voltage, V naught times e to the I omega t, and looking for a complex current as my answer. Okay? So when I use complex functions as my input and output, my differential equation doesn't change. It's still the same differential equation I'll use. It's still the same differential equation here I'll use. But the solution I look for, that will no longer be this. Instead, it'll be the complex version of this. So it'll be the current as a function of time is I naught times e to the I omega t, but I learned my lesson from last time. I should include a phase factor. It would be e to the I omega t plus phi. Okay? And by the way, this being a complex function means actually I have a way of writing this down in a simpler way than I could the real trigonometric functions. So I can write this down this way. I can do the exponential algebra and take out this phi as a multiplicative factor and say that this is equal to I naught times e to the I phi times e to the I omega t. Everyone okay with this expression here? Yeah, I just, so this is a nicer expression because I have a very simple looking time dependent function, and this is now just a simple constant. This alone will save a lot of unnecessary work. So let me plug this into my differential equation and rewrite my left-hand side. So my left-hand side would be, instead of having I naught, it will be I naught times e to the I phi. So I naught times e to the I phi. And when I take the derivative of this complex exponential, e to the I omega t, from chain rule, I get this factor of I omega. So instead of minus omega, I had to get a factor of I omega here from chain rule. Good. This is the left-hand side. I don't know, to me this looks simpler. Okay, so that's the left-hand side. Let me do the right-hand side and see if we can figure out if those two terms should be equal to each other. So the right-hand side is this. So, forgot to make this replacement in place. So this cosine of omega t should have been e to the I omega t. So the right-hand side here will be v naught over L. So this doesn't change. Cosine of omega t becomes e to the I omega t. And this term here becomes minus r over L times I naught e to the I phi. This is phase factor. And this is the place where you see why we call it phase factor, not phase addition. And then the I is a function of time again. So e to the I omega t. Good? So it's here where you can already see that this cuts down on a lot of the work that we had before. I no longer need this trigonometric identity because I can simply see that all three terms have the common factor of e to the I omega t. So whereas cosines and omegas didn't cancel, e to the I omega t cancels. It's the same function that occurs in all three terms. So I can cancel out e to the I omega t from each one of these terms. And what used to be all the complicated expression of separating out cosine omega t term, sine omega t term, and working it all out, it simply becomes the question of, is this complex number equal to this complex number? So let me write that out. So the two complex numbers we are trying to compare are these. I omega, I naught e to the I phi. Is this equal to v naught over L minus r times I naught over L e to the I phi? Good. All right. It feels like can I solve for I naught? Yeah, I think I can. So here, I can solve for I naught without ever needing to solve for e to the I phi. Let me show you how. So I naught is equal to, let me just move this term over here. I'm already going to do something that's a little bit sophisticated, so let me not skip steps. Let me move this over and then combine the like terms. Then I get I naught times I omega e to the I phi plus r e to the I phi over L. R e to the I phi over L. That is equal to, v naught over L. That. Let me solve this for I naught. And then I'll show you a mathematical trick that you can use to solve for I naught without ever solving for phi. So this becomes I naught is equal to V naught over L over all of this quantity, I omega e to the I phi plus R e to the I phi over L. Okay. Now, here it looks like the I naught depends on phi, right? And you remember from before that I naught here didn't depend on phi, right? So let me give you tell you a little trick that'll help you solve for I naught independently of phi without ever actually having to solve for phi. It has to do with understanding some properties of complex numbers. So we started out with a complex function, guessing a complex function answer. So here's my question. Is this I naught a complex number or a real number? Yeah, it's a bit of a tricky question to answer. Okay, let me rephrase the question. Can I choose my parameters in such a way that this I naught will be a real number? Yeah, I can do that. It essentially comes down to the correct choice of phi. So that this particular complex number that's here, it's the complex number written in polar form, with I naught being the magnitude, and e to the I phi having all the cosine theta plus I sine theta term in it. So I can make a correct choice of phi that'll make my I naught be real. So let me say my I naught it's a real number. Okay? So once you know that, then this is what I can say. If I take I naught absolute value squared, that this should be equal to simply I naught squared, right? Now, with a real number, these two are indistinguishable. They don't have any different meaning. But some of you might remember the difference in meaning between if you have a complex number z, if you take its absolute value squared, that's not going to be necessarily equal to simply g squared. Do people remember that? As in, imagine you have complex number g equal to a plus ib. You do get a different result whether you take what. So we are going to use this fact. If I naught is a real number, so when I take this absolute value squared, I'm simply going to get I squared. But this right-hand side is a complex number. So when I do the proper complex modulo squared operation, then I will get a number here that's hopefully going to end up being real. And I'll be able to associate with the I naught squared. And all I'll have to do is take a square root to get my final answer. So let's do that. So I'll do modulo squared for both sides. So left-hand side is very simple, nothing complicated. It's simply I naught squared. Right-hand side, I have to write it down with a little more care. And I'll just go through algebra carefully so that you can see it becomes what I hope it'll be. So it's the numerator, I'll just do it as it is. I don't have to, it's a real numerator, so I can just say numerator is a V naught squared over L squared divided by, and it's this denominator that I have to be careful with. So let me write down the complex conjugate first. The complex conjugate is, so for the complex conjugate, it's really a simple idea. Wherever you see I, turn it into minus I. And make sure that any number, any symbols you see are real numbers. Omega is real, R is real, L is real. So all I have to do is turn all the i's into minus I. Omega e to the minus I phi plus R e to the minus I phi over L times the original complex number itself. So times I omega e to the I phi plus R e to the I phi over L. Okay? Before I go far, do people already see that e to the I phi will cancel out? because I should have stopped and realized. I have the same e to the I phi term in both cases. So I can factor it out in both cases. E to the minus I phi here. So factor it out there. Times e to the I phi here. Factor it out there. E to the minus I phi times e to the I phi. What's that? The exponent is 0, so 1. Yeah. So e to the I phi factor simply all cancels out to 1. In fact, that's one of the things that this whole modulo squared thing is guaranteed to do. Now, what I'm hoping is that this minus I and I will get rid of each other as I go through the algebra. So let me do the denominator separately here. So what I have is minus I omega plus R over L. Actually, let me write it the same way I wrote it here. Then I can save me some math here. So R over L, the real part, first, minus the imaginary part, I omega. And the second term, the real part first, R over L plus I omega. That's the exact same thing I did here with R over L as A, omega as B. So this is equal to R squared over L squared plus omega squared. Good. Let me write that out here. New colors. I want to save the result here to refer to, but I can write down the simplified version of this up here. So the simplified version of this is I naught squared is equal to V naught squared over L squared over this thing here, R squared over L squared plus omega squared. Let me simplify. I have this L squared, absorb it into here. Then I have V naught squared over R squared, L squared cancels, plus omega squared, L squared. And to find I naught, instead of I naught squared, you take the square root. When you take the square root, this is what you get, or V naught squared becomes simply V naught, and the denominator becomes denominator's square root. Compare that with the result we got before. It's the exact same result, except it was quicker. I didn't have to go through the whole process of expanding out cosine and sine terms, and I didn't have to do that. So this complex, using complex exponential makes your algebra much simpler than it would be otherwise. So, or here's another way to put it. Complex exponential turns trigonometric expressions into exponential expressions. So in the places where you might have had to use trigonometric identities, all you have to do is exponential algebra. It's a much simpler task you have to do. For the, I guess the trade-off is that it is a more advanced concept. Like, it does involve becoming comfortable with a complex number and maybe knowing one additional operation that's defined in that context. But so this is the second method of doing this same circuit. So in both methods, this is the solution for time-dependent current, something that's oscillating at omega t plus a phase factor times a magnitude. And so in the interest of time, I won't do the phase factor here. But what you can see is that the magnitude works out to be the same using either of the two methods. All right, so let me do the third method. The third one is the simple one. It's the simplest one. And that's really the reason we introduce complex impedance. And what I'll tell you is that we don't have enough in-class time for me to demonstrate to you in every possible way. But I think I can tell you this much. I can tell you that even using complex exponential, much of this math becomes easier, so that Like I would never expect you to do something like this even in homework. It takes way too much time. There are too many ways of going wrong with it. Once you are using complex exponential, I think most of you can do this. It just, I mean, it's not easy like the one we are going to see now, but this is doable. So using this, you can actually work through all these circuits like you did a DC circuit. Because with the complex exponential, one of the things it does is it makes these calculus problems into an algebra problem. Because this e to the I omega t term will almost always cancel out. And this phase factor, you always absorb it into the constant coefficient in front. So I would encourage you to work out these examples, work out these calculations for other examples involving capacitor and LC circuits. There are questions in your homework where you can work through that and do that, convince yourself. What I'm going to do is, for the remaining 30 minutes, 40 minutes, is that with these expressions for voltage and this expression for current, I can simply use this, and it'll use this expression here, and it'll give me correct result. This is really the point of defining these complex impedances this way. These are defined in this way to make this expression true when you are driving with oscillating voltage or current, which is necessary to have a well-defined omega. Okay. So let me make myself some space here. So I'm not actually going to need any of this loop rule stuff. So I will get rid of the loop rule, and I guess get rid of everything here, except for the answers. I guess I want these answers out here. Yeah, I can get rid of this much. All right, so with these complex impedances, you work out the circuit problem like these were resistors. Even though inductor is not a resistor, but what you say is that you treat the inductor like a resistor with the impedance, with a resistance, I omega L. That's the impedance of the inductor. So let me, write it out. The current that's going through the circuit should be the voltage divided by the equivalent impedance. All right. If I'm treating this like a resistor, then it would be resistors in series. So this equivalent impedance would be impedance of a resistor plus impedance of the inductor. So this would be the voltage divided by impedance of resistor plus the impedance of inductor, I omega L. All right, I guess that's my answer. My current as a function of time is the voltage as a function of time, or V naught e to the I omega t divided by R plus I omega L. Now, staring at this, it may not look to you like right now that this answer is equivalent of this answer, or even the other thing that we wrote down before, that I as the complex function is equal to I naught, which was this, V naught over square root of omega squared L squared plus R squared times e to the I phi times e to the I omega t. If you are trying to compare this answer to these answers, right now it might not look quite like it. But this is the part where you have to carefully identify coefficients. So comparing this complex expression with this complex expression, with this e to the I omega term together, right? Which means this entire complex coefficient must be equal to not just I naught, because it's a complex number. I naught was supposed to be real. So this is equal to my I naught times e to the I phi. So this is the complex coefficient that's going to be equal to this quantity here. So what do I do to simply solve this for I naught? Not divided by exponential, because I don't know what phi is. Yeah?
For the exponential in the Euler's form?
No. It comes down to I don't know what phi is. So so this is the advanced aspect of this approach, because even though you have learned about complex numbers, you haven't been using them. So you don't know the basic operations dealing with them. I do the same thing I did here. I take the modulo squared. This modulo squared, what it does is it gets rid of any kind of complex phase factor. That's the whole point of this absolute value squared. So I do the exact same operation I did before, except this time it's simpler. So let me call this my left-hand side, call this my right-hand side. Actually, I probably should. Well, let me do it that way. So I'm going to take the absolute value square of the left-hand side, and when I do that, so it's a v naught over, this is the real and imaginary part. So it'll be v naught squared over r squared plus omega squared L squared, right? We say that's equal to the right-hand side, modulo squared. So here, let me write it out a little bit more carefully, because you have in this exact way it's written down before. I naught times, so first, let me write it down this way. So this will be written down with the complex conjugate times the original complex number itself. So the complex conjugate of this is I naught times e to the minus I phi. And here, the original number itself is I naught times e to the I phi. You see that e to the minus I phi cancels out e to the I phi. That is the whole point of the operation. Get rid of complex phase factors. So when you do that, what you end up with is I naught squared. So this is the same thing that we already knew before, that I naught is equal to square root of this entire quantity, which is v naught over square root of r squared plus omega squared L squared. So that's it. That's the answer. And let's see. Do I have time to go over? Might as well. So using this expression, you can actually solve for phi if you wanted to. So did you have a question?
I did. So when you have the left-hand side and the right-hand side came from a previous solution, right?
No, it's a way of expressing a number.
Oh, okay.
So I decided this is a complex number. And if I have a complex number g, there's two main ways you can express the complex number g. One is the Cartesian representation that you have seen before, a plus ib, x component to y component. And the other is the polar representation, which you write this as a real number times complex phase factor, e to the I phi. So I'm simply saying that this complex number can be written in this form, real number times e to the I phi. You are going to see this approach more and more in the upper division work. If you don't learn how to become familiar with this, you will continue to struggle. Because essentially, you are in a race where everyone knows how to drive a car and you are trying to run and This is more advanced tool. This is more sophisticated tool that makes your job easy. Like you can expect to compete with someone who's using power tools to build their house when you are using only hand tools. You have to be able to use power tools that everyone else is using. So anyways, I think I have enough time to actually show you how to work out this phase factor phi. It really comes down to the understanding this is the polar representation. So because, if you write out this e to the I phi using Euler's formula, then this is equal to r cosine phi plus I r sine phi. So the approach for solving for phi here is you take this entire complex number, try to express it in this Cartesian format, and when you take the y component or the imaginary component over the real component, imaginary component over the real component, that'll give you the magnitudes will cancel, and you'll get sine phi over cosine phi. So for a complex number g, this is an expression that you always have. You can always say, let's see, this phase factor phi, or rather tangent of this phi, is equal to the imaginary part of complex number divided by the real part of complex number. By the way, for this class, I'm not going to spend too much time on this phase factor. On an exam, I will always give you questions in a way that you can ignore the phase factor, and then if you can get the magnitudes, if you can get this, then that's good enough. But if you want to go one step further and find the phase factor, this is what you do. Take this complex number, you rationalize it so that you can express it in this format. Everyone here remember how to rationalize a number? Everyone here know how to rationalize a fraction? Okay, sorry, irrational fraction. How do you rationalize a fraction that has, let's say, square root on the bottom? Like if you have 2 over 1 plus root 3, how do you rationalize this? Yeah, conjugate 2 over 1 minus root 3. It's the same idea here. You multiply this by conjugate top and bottom. So I say this is equal to v naught over r plus I omega L times conjugate of this, except complex conjugate. R minus I omega L divided by r minus I omega L. The point of the complex conjugate is that when multiplied to the original number, it'll get rid of the imaginary part. So this will become, well, the same thing you've seen multiple times by now. V naught over, this thing is r squared plus omega squared L squared. R squared plus omega squared L squared times this. So let me actually write it out in one step. So the real part is v naught times r, and the imaginary part is minus I v naught times v naught omega L over r squared plus omega squared L squared. So when you take the ratio of B to A, actually this minus sign should be included into B. You take the ratio of B over A, that's the tangent of phi. And when you take the ratio of B over A, a lot of things will cancel out. The denominator will cancel out, v naught will cancel out, and you'll get only omega L and R. So doing that, you'll get tangent of phi is equal to minus omega L over R. And if you look back to our earlier result, that's the same result we got earlier with a much more complicated method. Or I guess much more time-consuming method. You could say this is equally complicated, but it's complicated in the matter of sophistication. It's a more sophisticated mathematical technique that'll save you a lot of time once you learn how to use it. That's really my justification for introducing it now. Once again, acknowledging that it's not standard topic. What I will tell you is that your textbook does have formulas for getting like this magnitude And one of the homework problem that I assigned from portable TA actually goes over those formulas. And you can memorize those formulas if you want. That'll get you the correct answers for the exam, or have it in your formula sheet. The method using complex exponentials and complex impedances is how to get those answers without having those formulas memorized. This is the only formula you would have to memorize. This is the only formula you would have to memorize. Yeah. With the square wave, all I'm doing is basically apply a sudden impulse and see the circuit response. What I want you to see is AC circuit. So with the AC circuit, you need to have a sinusoidally driven thing. And let me see if I can demonstrate something here. I think one thing I can demonstrate in simulation now and also in the circuit is this. I'm going to measure the voltage across the resistor. This way, what I measure will be a representation of current. This is something that's proportional to the current. And what you see now is that the place where the voltage peaks, that's my applied signal input, is different from the time when the current peaks. And this is what chapter 15 refers to as the phase factor or phase shift. And you'll have some homework questions on that too. And I guess one thing I can demonstrate now that's relatively easy is how this phase shift changes with the applied signal frequency. And I don't quite, let's see, I'm trying to remember. So the current is currently lagging the voltage, and I'm trying to remember if that means so my resonance frequency might be lower. This is one of those things where you just gotta try. Let me just change the frequency. Let's see. So when I go to higher frequency, yeah. Okay, so my current frequency that I'm at right now, 250 hertz, it's lower than what is the circuit resonance frequency. So let me increase the frequency, and as I do that, you see this output voltage go up. Yeah, and in fact, I need to change the scale back so that I can actually show the signal. Let's see, do I need to? Oh, okay, I need to change my frequency entirely. Yeah, and I need to change this more. Okay. Yeah, so I think I passed the resonance there. So let me, yeah. So this is what's called the RLC circuit resonance. The amount of current that's flowing through the circuit, it's frequency dependent. So right now I'm driving the circuit off resonance. So there's some amount of current flowing through, not that much. And as I near the resonance, what you see is that the current flowing through the circuit increases. And there's a point where it reaches a maximum. And you should see, I guess, yeah, because the way this is connected, it's inverted. So let me invert the channel so that it doesn't confuse me. Because this is what you should see. So as it reaches resonance, so the phase shift that you saw was reverse the sign. So current was, I think this is lagging, whatever. Current was on this side of the voltage, and as it goes through the resonance, you will see the peak go to the other side of voltage. So yeah, so around here is where it reaches resonance. So let me go to higher voltage so that I can show it. Go to higher voltage here so that it's not so imposing. Okay, so yeah, so this is the resonance. I'm just gonna click a few times. So this is on one side of resonance. The current is now getting smaller, and let me go to higher frequency. As I go to higher frequency, what you see is that the current increases until it reaches a maximum here. And then as I go to even higher frequency, the current actually decreases. So that's resonance. And one interesting thing you see is that on resonance, you see that the phase of the current and the voltage match up. They have the same phase. When the voltage is at maximum, current is at maximum. And in fact, if you calculate this value, it should be the applied voltage divided by the resistance. So what I want to demonstrate, I think it'll maybe take 10 minutes, is show this resonance with the real circuit. Let me just use all the same components. I'm just going to bring this 50 ohm resistor back, and that'll give us the resonant RLC circuit. All right, so I'm just going to plug this 50 ohm resistor back in. Fortunately, I didn't take out any capacitor or anything. And I'm going to get ready to measure the voltage across the resistor as a measure of the current. And the voltage here needs to be applied here. Okay, so it's driven, so yeah, the RLC circuit with the and what I need to change now is I need to change the driving signal into the sinusoidal signal, and with the sinusoidal signal, you see that the imperfections that I had before are gone, because this imperfection, it mostly has to do with this sudden change that I'm trying to drive. So when I'm not trying to do that anymore, I'm driving with a gentle sinusoidal signal. It behaves much more ideally. So, and when you're working with the AC signal, you will almost always be using just the sinusoidal signal. So yeah, and the output, the current that's going through the circuit, I do have something there, but it's a very, very tiny. It's this channel 1 is right now on the smallest scale. I think that's a 5 millivolts per division. So I think the resonance frequency was at higher end. So as I increase the frequency, what you see is that you see that current amplitude is going up. Oh, wait, I reached my limit there. Let me go to the other one. And let me go start at around the 500 hertz. Okay. So as I increase the frequency, the current is increasing. So let me change my scale here so that I can continue to display it. Increase the frequency, increase the frequency. Yeah, I still need to increase. So I'm gonna go up one more decade and then come back down to 5 kilohertz range so that I can properly go through the, okay, yeah. So I'm near the resonance here. Let me go through that. So so I need to go to smaller scale here. And now as I increase the frequency here, so there's a point where the voltage and current are in sync. They have the same phase. And that's also where, so let me turn off the input voltage so that no more voltage. All you're seeing here is the current. And that current goes through the maximum here. And the point where it goes through the maximum is where they are in sync. Lower than that frequency, it was current was, I don't know, leading the voltage or whatever. And after that frequency, the current is lagging the voltage. I always get those mixed up, leading and lagging. So I could have said it the other way around. So yeah, that's kind of what you get. Let me try to put these two in the same scale. So the input voltage at, I guess, let me just show the simulation here. And what I'm now trying to do is just to match my parameters of the input until my input kind of looks similar to the simulation input. I don't know if this matches up the way they are supposed to. Oh, that's too much. I think this thing is struggling to drive such a high voltage through the thing. So let me do it this way. I'm gonna decrease it. Let me just put this on 1 volt per division so that I can put in a more reasonable amount of volts. So input is at 1 volt per division. This is showing something like 4 volts peak to peak. And I'm gonna do something similar for the simulation. I'm just gonna Okay, so both the input and output are at 1 volt per division, and that's what's showing. Um, um, I don't know if that sounds right. In any case, let me turn both of these on, and they are both on 1 volt per division. And let me put this on resonance again. Oh, I guess that's right. Somehow I was expecting all of the applied voltage to be on resistor. Something's not quite matching the expectation here. Although I mean, what I say with the real thing somehow matches wonderfully well with the simulation. What am I missing? So on resonance, it should be that the impedance of the inductor and capacitor actually cancels out. So I mean that's why the maximum current is V in over R. What am I missing here? I'm trying to what it is that I'm not thinking. Because I mean, in the experiment it works fine, and somehow the simulation matches. So I don't think simulation is doing something that's wrong. It's just that it wasn't quite matching what I was expecting it to do. Um, why is it different by I mean, let me just try this just to, yeah, somehow on resonance, the value of the resistance shouldn't matter. Oh, you know what? I think I know what it is. This simulation, which is wonderfully, it's simulating the output impedance of the function generator. So 50 ohm is the standard output impedance of a lot of instruments. So even though in the circuit you have 50 ohm resistor, what you what your real circuit actually has is another 50 ohm resistor across this connection here, and so or another not across where I was pointing it, but there's a yeah. So this has output impedance of 50 ohm. That actually does explain this factor of a half. So if this resistor is higher, which makes the output impedance of the function generator less relevant, then the output signal matches the input signal more. So let me just confirm that with the real circuit here by replacing my 50 ohm resistor with a 500 ohm resistor, which I don't really have, but I do have a 750 ohm resistor. So let me do with that, and that should give me something that's pretty close. So this is my it's coming out of a box that's labeled 750. Either way, I'm gonna measure it, so it doesn't actually matter what it is. I mean, what the box is labeled. It matters what the resistor is, and I'm gonna measure it so that I know what it is. Okay, 7 something, 767, but out of 750 bucks. So let me replace that register with, or use that to replace the 50 ohm register. And yeah, and what I get matches what it should look like. So, and let me just go through the resonance again to show, oops. So yeah, so that's on the higher frequency side of the resonance, and on the lower frequency side, this is what it. Why does it? Oh, I guess that's the lowest I can go. It doesn't go any lower. So yeah, so yeah, that that explains it. So and I think this simulation is pretty good for giving you that realistic experience for what that looks like, because it simulates enough components of a real experiment. And I'll also have a set of instruction for using the other simulation, the FET simulation, where it's less realistic, but it's more versatile in terms of the circuit you can try.